very, very important, looking here, that you can identify the shape so that you can identify the polarity and then eventually get to the intermolecular force. Okay? So just to remember here, the direction of the polar bond in a molecule points towards the more electronegative element. That's called a dipole moment. In this case, HCl only has 2 atoms. Remember, it's going to be linear then. If it only has 2 atoms, you can only go from point A to point B. Chlorine has a much higher electronegativity value than hydrogen, and therefore the electrons are going to spend more time around the chlorine than they do around the hydrogen, creating a partial negative charge over here. Okay? Partial negative charge on that side, and then around the hydrogen side is more of a partial positive, creating a dipole. Okay? So that's one thing that we need to look here, is looking for the dipole moments, because not only does it depend on the dipole moments, but it also depends on the shape. Because remember, if the dipole moments cancel themselves out, then it's symmetrical, and therefore the entire shape is rendered nonpolar. Okay? So nonpolar molecules, the dipole moments are symmetrical and cancel out. An example here of boron trifluoride, remember in this case boron forms this trigonal planar shape because it only needs 6 valence electrons. It's one of those weird exceptions. But as you can see, the fluorines are all equally pulling on the electrons. So no particular side of the molecule has a partial charge, and therefore is going to be nonpolar. Polar molecules' dipole moments are asymmetrical and don't cancel out. In the instance of water here, the dipole moments are going to point towards the oxygen, the higher electronegative element. So this side of the molecule by the oxygen is the partial negative, and the hydrogen sides are going to be partially positive. Also, the shape of water is bent, has lone pairs on the central atom of oxygen, which is going to indicate to you that it is not symmetrical, and therefore is going to throw off the idea of being nonpolar. Symmetry is off due to the lone pairs. The dipole moments pull towards the oxygen, and therefore this would be polar. All right, therefore polar molecules have asymmetrical shape or lone pairs, okay, or they have ligands that are not all identical. So in this particular example, CHCl3, you have 1 hydrogen and 3 chlorines as your ligands. They are not identical ligands. Therefore, it's going to throw off the symmetry of the molecule. The dipole moments go towards the chlorines anyways, and because they're more electronegative. So that side of the molecule is going to be partially. Over down here will be the partial negative. Can't see that. Over here is going to be the partial positive. Okay. Okay, clues to polarity again. Tetrahedral trigonal planars are going to be nonpolar if their ligands are the same. Okay, linear shapes tend to be nonpolar as long as you have symmetrical ligands, same kind of ligands like CO2 there. Molecules with lone pairs like trigonal pyramidals or bent shaped ones are always going to be polar because the lone pairs throw off the symmetry. Okay. We don't really need to complete this because this was already in some of your examples. But now, being able to identify the shape and the symmetry so you can identify polarity is important in determining the intermolecular force, or I guess I should say the strongest intermolecular force involved in the molecule. Now, chemical bonds join within the molecules. So, like for instance here with water, this is an example of water here. We have our oxygen. We have our hydrogens. This bond right here, okay, to here, that is a covalent bond. It's called an intramolecular force. Intra because it's inside the molecule itself. Now, that's just a regular covalent bond. That's not what we're talking about here. What we're talking about is if we had 2 separate waters here, what is going to attract them to each other? I mean, how do we have like a glass of water where all the water molecules are sticking to each other? Well, there's forces between them holding them together. And I'm sure you did this last year in biology where you maybe did the dropper on the top of the penny and it formed a nice little bubble, and or you went over, say, like surface tension and how the little bugs can float on the top of water. That's all because of these intermolecular forces. The water is sticking to itself. It's cohesive. Okay, I think that was the correct term from biology. Cohesive, sticking to itself, adhesive, sticking to other things. So these are what we're talking about, is like actual stuff sticking to itself. Okay, intermolecular forces between molecules, not within the molecule itself. This is between the molecules. Okay, so we have three types. London dispersion forces. You can see it as LDF, London dispersion forces. Sometimes in general they just call them dispersion forces. So they might drop the London part off, just so you know. There are dipole forces, and then there's hydrogen bonding, which you're familiar with, which of course is very much a misnomer because hydrogen bonding is not bonding. It is actually an intermolecular force. Gives you kind of an idea that some people think it actually involves inside the molecule. No, hydrogen bonding is outside the molecule. It is a type of intermolecular force, and people get confused about that. Now, London dispersion force is an attraction between two instantaneous dipoles, or temporary dipoles I like to call them. That is due to an asymmetrical electron distribution. All atoms and molecules engage in London dispersion forces. Why? Because London dispersion forces involve the electron clouds, and any molecule or any atom is going to have an electron cloud. So say if I have an electron cloud around me and I get near a student over here that also has an electron cloud around them, my electron cloud is going to repel this other electron cloud, and the electrons are going to move away from each other. They're going to repel each other. So they're forming these instantaneous dipole. So just by being near another electron cloud, I'm forming a dipole, or my cloud would be forming a dipole. The second I go away from it, it goes back to normal. That's why they're instantaneous or temporary. They don't last very long. And that's why they're also very weak, because it creates the dipole as quickly as the dipole goes away. You have to be near something with an electron cloud to create the dipole. When you're not, then it goes away, and then you don't really have any force holding it together. So these guys are going to be very weak. They're going to have low boiling and melting points, okay, because they don't have a whole lot of strength holding them together. Dipole forces, attraction between two permanent dipoles. So anything that's polar is going to also have dipole forces, because they are a permanent dipole, like water, like SO2, like NH3. Anything with that is, is going to be polar because of its shape, it's going to fall into the dipole category. London dispersion forces, those ones are all nonpolar molecules or atoms, like even helium and neon, even though they don't bond with anything, they have electron clouds, so they fall under London dispersion forces and can form temporary dipoles. Hydrogen bonding, though, is a specific type of dipole that is stronger, but it only involves three particular combinations. And that's because hydrogen is so small that it only works with these three, and the electronegativity differences are very high. So it's HF, HO, or HN if you see any of those bonds in the molecule, but it has to be H to F, H to O, or H to N. We call it H-FON. Then it's going to form, in addition to the dipole forces, the additional hydrogen bonding. And that's going to make it a little bit stronger because it's more polarized. You're going to get more of a larger distribution in your partial charge, so it's going to make it stronger. So keep in mind the hydrogen bonding only happens with HF, HO, or HN. You're not going to see it like HCl doesn't work. The electronegativity difference is not high enough. HS is not high enough, the electronegativity difference. So it's only HF, HO, or HN, so that's why we call it H-FON. H-FON, having FON with H. There you go. So, London dispersion forces, weak forces caused by instantaneous dipole. Electron distribution becomes asymmetrical. And this is the only force of attraction that exists among noble gases or nonpolar molecules. But you'll see that nonpolar molecules and noble gases, things like that, they're pretty much gases or liquids at room temperature because they don't have a whole lot of forces holding them together. And you can relate the phase to it because the strength of the intermolecular force, if it's a stronger force, it's more likely to be a solid or a liquid because, you know, you have these things attracting to itself and therefore keeping the phase in check. Okay, so here it's showing you like you had atom A and atom B. Here's an example, atom A and atom B. They have their two separate electron clouds. Well, atom A now approaches atom B, or atom B is approaching atom A, so it's making the electrons come over here on this side because of the electron cloud over here. It's making the other electrons want to go away from them. And when it does that, it creates a partial negative charge on that side and a partial positive charge on this side. And then, you know, more atoms come in and then you create more dipoles and more attractive forces. So keep in mind that though, as quickly as they are next to each other and as they are get further away from each other, then that force and that cloud readjusts back to its normal state. Okay? So molecule A, molecule B, this is just showing H2. So you can see H2 here. Okay? When they're separate by themselves, they have their nice oval-shaped electron cloud. But if they get close to one another, here we're saying molecule B is getting close to molecule A. So the electrons shift and move over to the other side of the molecule to get away from this electron cloud, forming the temporary dipole with a partial negative and a partial positive charge. And therefore, we get these instantaneous or temporary dipoles. Like I said, they're very fleeting. They don't last very long. They're not very strong. That's why you're going to see these guys having low boiling and melting points. And not any of the fun extra properties like high surface tension or things like that either. Okay, so just some more pictures here. These temporary dipoles, the shifting of the cloud. But like I said, as quickly as it happens, it quickly can go away. They're instantaneous. It's not going to show it. All right. So dipole forces are the ones with permanent dipoles. So they already have a positive and negative end automatically. So the positive end of this one will attract a negative end of another. The positive end will attract a negative end, and so forth. Now, this is for everything that is a permanent dipole is going to have dipole forces. In addition to the London dispersion, everything has London dispersion forces. But the dipole force is considered the stronger force, so that's the one you're going to name in the problem. That's the way the problems are phrased. They're going to say something like, name the strongest intermolecular force that this molecule is going to have. So yes, all of them are going to have London dispersion, but in a particular case, it might have dipole or hydrogen bonding, and you would need to name those. So we're just looking at the ones that automatically have positive and negative ends. They are the polar ones that have asymmetrical shape. Okay, dipole forces. I don't know if the animation's going to work, but we'll see. They line themselves up based off of the poles. So the positive ends attract the negative ends and so forth. And as you can see, they're forming a nice little pattern now. Hydrogen bonding is a type of dipole force that is stronger, but it only applies in molecules where you see HF, HO, or HN. And the H has to be bonded to the F, H has to be bonded to the O, H has to be bonded to the N. You can't have, one where the C is in the middle, H to C, and then an F also to the C. No. Has to actually be between the H and the F in order for hydrogen bonding to occur, and obviously that occurs in water. And that gives water all of its lovely special properties, the high heat of vaporization, the high surface tension, the higher boiling point, okay? Things like that. Hydrogen bonding, once again, this one's showing you water over here. This one is an organic molecule where it has an NH group off of it. So as you can see, the NH group here is going to form attractive forces over there to the O. And you've heard of hydrogen bonding too in DNA because that's what does the base pairing of the ladder. The hydrogen bonding between like the A and the T and the C's and the G's. That's all created because there's lots of NH bonding in those amino acids. Okay, there's a picture of that hydrogen bonding of the DNA molecule up the ladder. But remember that the amino acids have lots of NH groups in them, and H to N is under the H bond, so that would be falling under the hydrogen bonding. Okay, so determining the IMF. For this particular example, NCl3. Well, I know it's a group 15 central atom, and I know this has 3 ligands attached, so what else is going to be on the central atom then? A lone pair. Now, if you can't look at the formula and recognize that this one's going to be trigonal pyramidal, like I can look at it and go, oh, 3 ligands, nitrogen's in the middle, it's going to have a lone pair and 3 things attached. Draw it out. You know, go ahead and take a moment to quickly draw it out. Because this is going to be NCl, like so. You can draw it out and go, oh yes, 3 things attached. 1 lone pair, this one's going to be T pyramidal. Okay, then I know, oh, everything that's T pyramidal happens to be asymmetrical because it has a lone pair. Therefore, it's going to fall under the polar category. So, its strongest force is either going to be dipole, or hydrogen bonding. So I have to evaluate this point. Do I see any H's in there? No, so it can't be hydrogen bonding. So its strongest intermolecular force is going to be dipole. Okay, looking here, CH4. Can anybody tell me what shape that one's going to be? Tetrahedral, very good. Are all the ligands the same? Yes, so it's going to be what? Polar or nonpolar? Nonpolar, so what's the only force it's going to have? London dispersion forces. Good. Okay. HF. What type of shape we got here? 2 atoms is always linear, and we know that they're not the same atoms, so is it going to be polar or nonpolar? Polar, it's definitely asymmetrical, and so therefore it's going to have dipole forces automatically. So then we look to hydrogen bonding. Is it HF, HO, or HN? It's HF, so it's definitely hydrogen bonding. Okay, so this one has London dispersion, dipole, and hydrogen bonding, but usually they'll ask for the strongest force, and the strongest force would be hydrogen bonding at that point. Okay? Which do you expect to have the higher boiling point and melting point, and why? HF, very good, because it has the strongest intermolecular force, so it has the strongest cohesiveness, holding it together. Those forces have to be overcome in order to separate and spread out. So in order to go from a solid to a liquid, those hydrogen bonds between the HF, those have to be overcome by heat in order for them to spread out and become a liquid. Then, if we want it to become a gas, guess what? You have to add more heat because you have to overcome all the intermolecular forces for it to become a gas. Okay, because gases don't have intermolecular forces, they're randomly bouncing around their container, hitting the walls of the container. Okay, so the strength of the intermolecular force, the higher the boiling and melting point. Okay, because they'll be asking you to do that on your worksheet. So let's go ahead and do a couple examples. Okay, so on the front here, it kind of summarized the notes in the PowerPoint for you, showing you that, like, example of the HCl dipole attraction, the permanent dipoles because they are polar. Okay, hydrogen bonds. Here showing you water again, and then the London dispersion with the temporary dipoles, weakest intermolecular force. One other thing I want to point out before we move on. The ionic bonds remember, are the full charge transfer, and they form those lattice structures. So that is what holds it together there, and it's very strong. So that's why they have super high boiling and melting points. Metallic bonds have those C of D localized electrons around their positively charged nuclei. That also is what holds the metal together. Why do you have a sheet of aluminum foil? But it's pretty much those full charges of attraction. So ionic bonds and metallic bonds, in terms of strength, are way stronger than hydrogen bonding or dipole-dipole forces or London dispersion forces. So keep in mind, in terms of the scheme of things, in terms of boiling melting points, metals and ionic compounds are going to be dramatically higher than anything covalent. Okay? All right, just wanted to point that out. So here's a nice little flow chart. Is the compound covalent? No. If it's a compound, it's got to be an ionic compound, and therefore it's going to fall under there, because if it was just a metal, it would only be the metal. Now, the next thing you ask yourself, is the molecule polar? You look at its shape, you decide if it's polar or nonpolar. If it is not polar, it automatically only has London dispersion forces. Then, following the flow chart, does the compound contain hydrogen and H, O, or F? But be careful, remember the hydrogen has to be bonded to the H or the O or the F. It can't be bonded to something else and then have another one of those atoms in the molecule. So, if it doesn't have H-FON in there, it's automatically the strongest force is going to be dipole-dipole. And then if it does have H-FON in there, the strongest force that it contains is hydrogen bonding. Put some other examples down here for you to follow. Similar to the PowerPoint, like here, H to S, this is a bent-shaped molecule. Drew the, like, not only the Lewis dot structure, but also the shape kind of in the way that it was drawn. Polar covalent molecule, dipole-dipole IMF, because it's H to S, doesn't fit the definition for hydrogen bonding. CF4, all the ligands are the same, it's tetrahedral, so that's London dispersion. Here we're looking at ammonia, NH3. It's a polar molecule, it's pyramidal, and has H to N. There is a bond between H to N, so it does fall under the hydrogen bonding category. Okay? Now here, basically, what you're going to do is for each compound, identify the intramolecular forces either as ionic or covalent. And then if it's covalent, then draw the Lewis dot structure. Identify the shape and list the strongest intermolecular force. So that's the first thing to look at here. We have SCl2, ionic or covalent? Covalent. How do I know it's covalent automatically? It's all nonmetals, right? Remember, we're looking for all nonmetals here. Then you would draw it, and you could count up the electrons and do all that, but I'm going to quickly go ahead and draw it. If you added it up, there would have been 6 electrons for sulfur, 7 for each chlorine, and it ends up what shape here? Bent, thank you. This is a bent-shaped molecule. It has 2 things attached and lone pairs on the central atom, so therefore it's going to be bent. So is it polar or nonpolar? It's polar, good. So what's going to be its strongest intermolecular force? Dipole, dipole. So this is what we write for short. Dip, dip. And you can put H bonding. Dip, dip, H bonding, LDF. That's how we abbreviate. Okay? That's what I want to see here. And then on the other sheet that you have here, this one has a nice also provided flow chart for you to follow. Okay? But this is supposed to be honing in your skills of being able to look at the formula to help you identify the shape immediately. Then you can identify the force. So try to follow how the shape is identified based off of the formula here. CCl4, that's tetrahedral. Tetrahedral ligands are the same, going to be nonpolar. Nonpolar means what's its strongest intermolecular force? LDF, right? Tells me this one's bent, so it's automatically what? Polar. Now I look inside the molecule. Do I see H-FON? NO2 does not have H-FON, so it's automatically what? Dip, dip. Okay? How about, oh, this one's a good one, HCN. Let's think about this. It's linear. That's number 6 here. Let's look at number 6. It's linear. Are the ligands the same? No, so it's automatically polar. Now, it's polar, but look at the configuration. Do you have H-FON there? No, because what's bonded to each other? H is bonded to the C, which is in turn bonded to the N. So the H and N aren't exactly bonded to each other, therefore it is not, this does not fall under hydrogen bonding. This is going to be dipole-dipole. Okay? So pay attention, close attention to that kind of stuff. Where is the bond? Because if it's not directly between HF, HO, or HN, if there's a C in the middle or something, no, it does not fit the definition for hydrogen bonding. Okay? Good with that? All right, so I'm going to let you practice, then we'll come back and ask questions in a minute.